Hi, my name is Tom Manning, and I'm a faculty member in the chemistry department at Valdosta State University. I'd like to tell you about an educational philosophy that I'm excited about. First, I'd like to go back in time a little bit and tell you about a project I was involved in the 5th grade. I was in New York City, and I wanted to do my science fair project on octopuses, or octopi. The problem is, in New York City, there are no octopuses or octopi. And in an era where there was no Amazon, no eBay, no FedEx, etc., I had to come up with a way to get them. So I sat down and wrote 3 letters. 2 went to marine labs in Florida, and the 3rd went to a marine lab in Italy. Within a month, I got 3 boxes back. They all contained octopi/octopus in formaldehyde and beaks, and one even had a small container of the dye that octopus shoot out. So for a 5th grader working on a science project that was infatuated with the ocean, I had paid her. But another thing happened was that this was my first project, the first time I had my own idea and I followed through on it. And it was something I was passionate about. And to this day, I remember the details of that in great detail. So I'd like to take this experience and fast forward to what I'm doing with students today. So I'd like to do projects with students that have several facets involved. First is we're trying to solve a problem. We're not just studying what the problems are or what other people have done. We're trying to solve the problem. We take on significant problems that range from environmental conditions to new drugs. We consider the economics of the situation. Many of the things that we're dealing with, you have to be able to scale up and do it on a large scale. So if we come up with an obscure solution to a problem, but it costs way too much money, I think we've wasted our time. We want to do something that we call meet peer review. This is where when students are done with a project, that it gets approved by the US Patent Office or it gets published in a journal. This way we know that we have outside professional opinions that say what you did with your students is good work. There has to be a sense of adventure to it. Right? I'm not a big believer that you have to be standing in front of a lab bench 60 hours a week doing the same thing over and over and over again and going through mind-numbing motions. There should be a sense of let's help the world. And what I really want to emphasize is I'm doing this with undergraduate students at a school that has no graduate program. Why that's significant is because we don't have tremendous amounts of technology. Our students cannot work 60 hours a week. We don't have big grants. We have to focus on simple, clever ideas to solve the problem. And so a lot of times we might think about something for a year or 2, have different students try different things until we come up with a solution. Then we have to optimize our solution. So let me tell you about a drug called Bryostat. It was originally extracted from a marine organism called Bugula narentina, which is found in the ocean. The problem is it takes 14 tons of this obscure critter to get less than half an ounce of the drug. It's only found in certain locations, it's seasonal, and when you typically do find it, you find a small piece that might be the size of your hand. Now what's so great about Bryostat is it actually has been shown to cure or to reverse or slow down certain neurological diseases. It attacks HIV reservoirs that retrovirals just suppress but do not knock out. It also has strong anti-cancer properties. So many of the elite organic chemistry research groups that are in universities have been focusing on the synthesis of this molecule, and they've been successful. They can synthesize it, but the amount of steps, the amount of technology that are needed, and the time scales make it impractical to hit a world supply. Right now, Bryostat sells for about $15 million a gram. Okay, so the synthesis have been published for at least 20 to 25 years, but they are not practical. So we want to come up with a simple solution to make Bryostat. So we go back to the ocean, right? And what we do is we study how the bacteria that live inside Bugula, the chemical conditions they're comfortable with, as well as the biological and physical conditions. And then we replicate those. And we have to have the right spot, the right time of year, the right bottom. We have to grow it on the right surface, and we have to use the right nutrients. And if we do that, we get Bryostat. And you can tell by the buckets that the 2 students there are using that we are not using high technology. We're basically farming to ocean to make this drug. So we've published papers on this, a number of papers, maybe 10 or 12. We filed the US patent application, and now we're working with 2 companies to purify it. Let me tell you about coral restoration. Right? Worldwide, corals are under attack by human interaction. This ranges from pollution to climate change. So what we have been working on developing is a material or surface that will send out a chemical cue and attract coral larvae to settle on it. Once they're there, there's nutrients built into that material that slowly release and give a healthy diet to the young coral. You can see there in the upper right-hand corner, there's one of the corals that we grew in the Florida Keys. We have a permit from NOAA to do coral restoration in the Florida Keys National Marine Sanctuary. As you can tell by this group of students that are getting ready to make a whole bunch of coral restoration material, that it's a project a lot of people like working on, and we're constantly making changes and improvements to everything from geometry to chemical composition to where we place it. And so far we've been successful. Our goal here is a large-scale production of an inexpensive green tech material where the students do most of the development. So as the students go through this, they're learning about patents, they're learning about prices, they're learning about government regulations, right? They're learning how to function in the real world. They're also learning how to make concrete, which I think is a pretty good thing to learn. Tuberculosis is one of the great killers in the history of humanity. Antibiotic resistance is now becoming a big deal with many bacterial infections, including TB. Right now on planet Earth, approximately 2 billion people have tuberculosis. But the biggest concern isn't the latent form or even the active form, it's the drug-resistant forms. So working with undergraduates, we said, how can we solve this problem? Right? A lot of the students want to go to medical school, they want to go to pharmacy school, they want to go to graduate school and study drugs, or they want to study microbiology or genetics. So this is a great project to learn a lot from. But it also is, can we come up with a solution? So what we did was we took existing antibiotics that no longer worked, but were very inexpensive and well understood by the medical community, and we repackaged them, almost like a Trojan horse. And then when we give this drug to that bacteria, the TB bacteria, right, it doesn't recognize it. Its immune system does not recognize the structure, and it takes it up and it works. So we developed a method of repurposing existing antibiotics to make them work again, and we received a patent on it. So you're not going to find too many undergraduates that are patenting new drugs. Oysters. When I say oysters, people think of food. Right? We're not doing this for food. Oysters are a keystone species that play a critical role in shoreline erosion, controlling it, in providing habitat for all sorts of species, and for filtering water. Did you know that one oyster can filter up to 50 gallons of water a day? So imagine an oyster bar that has 10 million oysters on it, gosh, or a bay that has 1 billion oysters in it. All the co-authors on this paper, which was recently published, are undergraduates, and they worked along the way as we developed this material, like the coral restoration, that attracts natural oyster larvae, called spat, to its surface, and then gives them a nutrient to help them grow faster. So these oysters can grow faster than they do without the material. And as you can see here, where we're on a mud flat, you can grow them in places that oysters typically would not grow. So STP solved the problem, environmental problem, right? Worldwide shoreline erosion, and being a keystone species is a critical problem. 85% of the oysters worldwide are gone from what they were 200 years ago, and the Chesapeake Bay has lost 99% of their oysters. So that gives you an idea of the scale of the problem. So we have to have a simple economic solution that works. Cancer. Obviously one of the most dreaded words that anyone ever hears if they go to a doctor. It's even worse in a third world or developing country because they often don't have the medicines to treat it. So we have developed 20 new drugs that have entered preclinical trials, and probably 12 to 14 of those were kind of a modification approach until it got better and better, until we got where we are now. Right, so we've published a number of papers, and we filed a patent application with the students. What do the students get out of this? This is a discovery process. This is not a canned lab. We go in and we make something. We don't know if it's going to make the crystal that we want. We don't know if it's going to be accepted for testing. If it is testing, we don't know what the results are. Many labs that you do in academics, if you follow the instructions, you get the right answer. There is no right answer to this, there's just the answer that we get. And so along the way, what we have focused on, we've narrowed our field to cervical cancer that's caused by HPV that's impacting developing countries. Why? Because HPV is now the leading STD on the planet, and roughly 60% of all STDs are HPV. And on top of that, last year over 300,000 women died from cervical cancer that was correlated with HPV. So we are trying to develop, or have developed, but it's still in its early stages, a drug that can be used for cervical cancer in a developing country in an economical fashion. So let me explain this picture. It was just taken a few weeks ago. The man in the middle with the blue tie is Congressman Carter. He is the only pharmacist in the US Congress, which gives some kind of a unique perspective on a combination of laws, budgets, drug companies, and what is actually sold. He owns 3 pharmacies in Savannah, Georgia. The 9 students you see there just gave him a presentation. They talked about their projects with developing a new malaria drug, developing new antibiotics, developing cancer drugs, developing the TB drugs. But they also talked about was an implant, all right, or delivering a drug. Again, thinking of a developing country where rather than taking, for example, for TB, 5 to 7 large pills a day, that if you have an implant that's located very close to the diseased area that is biodegradable, it does not have to be removed, and it costs less than $1, and it delivers the drug at a certain rate, that you have made a great breakthrough in terms of minimizing side effects, cost, and doctor's visits. In developing countries, just like the US and Western Europe, a lot of people start antibiotic regimens and do not finish them. With a biodegradable implant, we hope to overcome this problem. And we've done this by using very economical materials that are very easy to work with. So what's this talk about? This talk is about taking education from being just PowerPoint slides, online tests, multiple choice tests, saying here's a problem, let's solve it. We're not going to solve all the problems, but as the students learn to attack problems, and they learn about regulations, and they learn about economics, and they learn about working with their hands, and they working in groups, they become better citizens. And our success to date, close to 100 papers published in the peer-reviewed journals by chemistry and biology students at Valdosta State working with me, I think is proof that this has some validity to it as opposed to a normal education. Thank you very much.